Hello, in this video lesson we will talk about gas chromatography. If you haven't watched our video lessons on chromatography in general and HPLC, I strongly recommend you to watch those videos. Uh, Otherwise, okay, understanding gas chromatography may not be easy for you. So please watch first chromatography video lesson in which we describe it, the column chromatography and thin layer chromatography, and HPLC video lesson, which was quite, let's say, informative. So this video lesson is about gas chromatography. Here we go. Gas chromatographers have this kind of, let's say, shape linked to monitor and computer processing part. It is an analytical technique that is used to separate and analyze volatile compounds. Because it is gas chromatography, it's widely used in chemistry, industry, pharmaceutics, and environmental analysis in food chemistry and other branches of research and application. Gas chromatography is a technique in which the gas phase analyte is transported through the column by a carrier gas, which can be helium, nitrogen, or hydrogen. Therefore, it is expected to be not expensive. I mean, carrying out the experiments is not as expensive as HPLC, I would say. The separation technique may occur by gas-solid absorption. We are going to talk about absorption in other mechanisms, where the analyte is absorbed by the solid particles that constitute the stationary phase, or by gas-liquid partition. We will talk about gas-liquid partition as well, in which the stationary phase is a non-volatile liquid. Generally, gas chromatography is associated with a mass spectrometer. The combined version is called GCMS, gas chromatography mass spectrometer. It is possible to observe the fragmentation pattern of compounds of a given sample and then establish their composition by comparing the mass spectra available in instrument database. So in most cases, we can see gas chromatographers linked to mass spectrometers as LC-MS or GC-MS types of mass spectrometers. Okay. The principles of gas chromatography is, let's say, quite simple compared to HPLC. I would say it is simpler. Here we can see that gas chromatography is consisted of carrier gas container, gas flow pressure regulator, injector, yeah, sampling tool, let's say, and the column has this kind of shapes in gas chromatographers, and the detectors link it to computing, let's say, tool, data analysis tool. Separation based on volatility and interaction with the stationary phase. The sample is vaporized and carried by an inert gas, as we talked earlier. We can use helium, nitrogen, or hydrogen as carrier gas. Components travel at different speeds and separation based on the traveling. The separation occurs there, and the traveling speed comes from the interactions between the matrix, from the interaction between the matrix and the compounds to be separated. A mixture of compounds can be separated using GC with a flame ionization detector. There are different types of detectors. We are going to talk about detectors a bit later. And the compounds can be identified using pure compounds of the pure standards of compounds of interest. As we use standards in HPLC here, we can use these standards as well. But the advantage of the GC over HPLC is that even without these standards, it is possible to identify the compounds. The GC has its own database, and from the database, the signals with their molecular mass and charge ratio can be identified. So with this feature, GC is expected more, let's say, effective in terms of identification of new compounds, in terms of identification of compounds. With the standard analytical curve, it's possible to use the technique to identify the chemical constituents of interest. Okay, the credit for the invention of gas chromatography goes to Anthony J. James and Arthur J.P. in 1952. Gas chromatography is based on the basic principle of partition chromatography rather than absorption chromatography. Okay, we talked about absorption chromatography and partition chromatography in our chromatography video lesson. As a small reminder, let me tell you that absorption chromatography is about the absorption on the surface of the matrix, on the surface of the sorbents, and partition chromatography is based on the solubility of the getting separated compounds within the mobile phase, let's say. The separation of compounds is based on the different strength of interaction of the compounds with the stationary phase, like dissolve-like rule. The stronger the interaction, the longer the compound interacts with the stationary phase, and the more time it takes to migrate through the column. Okay, about the affinity, we talked in our column chromatography, in general chromatography video lesson. The main power that results different flowing time of compounds in HPLC or in column chromatography is resulted from the interactions of the compounds being separated and the matrix. Similar, let's say, mechanism is expected here in this case in GC as well, but the difference between gas chromatography and liquid chromatography is that here we use gas as mobile phase. And longer columns provide more time during which partitioning and thus separation can occur. This is especially needed for the separation of compounds with similar functional groups. We are going to talk about functional groups a bit later. So again, the mechanism is not very, let's say, complex. This is the gas carrier tank, yeah, pressure regulator, flow controller, sample injecting point, yeah, and then column, it differs in length. We will talk about this, and different detectors are provided there. So then the obtained results can be shown to us on the display. Okay, these are about the gas chromatography columns. Now we are going to see types of gas chromatography columns. There are two different types of gas chromatography columns. The first one is packed columns, and the second one is capillary columns. There could be some different types that could take some elements of both of them, but these are two main different types of gas chromatography columns. Okay, the first one is packed columns. These packed columns are traditional columns filled with solid packing material. We will see some models in figures. And capillary columns have this kind of shape, this kind of okay, cyclic shape. And capillary columns prevail, columns made of fused silica with a thin internal coating. Here we can see the differences between packed columns and capillary columns, and the main difference is in their length, as indicated here. The packed column is around 4 or 5 meters. I mean, internal diameter is about 2 to 4 millimeter, and in capillary column, it's about internal diameter is about 0.1, 0.53 millimeter. And in length, okay, in packed, we can see the length between 0.5 to 5 meters. and the capillary columns can reach from 5 to 100 meters. In general, okay, it is expected to be 25, 30 meters. And the column material also differ in these two columns, and the packed columns are made of stainless steel or glass, and capillary columns are fused silica or stainless materials. By the efficacy, we say that capillary columns are more effective. Okay, mobile and stationary phases are carrier gas, as we mentioned earlier, and stationary phase can be liquid coated on solid support or solid adsorbent. We will see some figures further. And this is an example to packed column made of stainless steel or glass tube filled with particulate packing material and adsorbent material or support material coated or impregnated with a solid phase. Here we can see different sizes of the adsorbent. So on the surface of these particles, gas compounds can be kept for a few seconds. So then we can witness the separation of different compounds based on the interactions of the compounds being separated and the adsorbent. And there is a contribution of the hole size on the surface of the sorbent material as well. Internal diameter, again, in packed columns is between 2 to 4 millimeter. The length is between 0.5 to 5 meters. Packing supporting material with 0.5 to 25% liquid phase, partition material, or no liquid phase, absorbent material. Yeah, and liquid phase can be multiple types available. So there could be columns filled with liquid, or the columns without the liquid. And this is a capillary column. Internal diameter can be 0.1, 0.25, 0.32, or 0.53 millimeters in practice. The length, again, can reach 100 meters, in most cases around 30 meters. And the materials are fused silica glass and liquid phase provide good separation, but less variety than packed columns. Here we can see this is a fused silica or stainless material, and inside we can see the liquid phase. And plot column contains immobilized porous polymer, alumina, etc. Yeah. A typical column, capillary column, is a thin fused silica glass tube lined with a liquid phase or absorbent material or having a chemical bonding layer. These metal tubes are also sometimes used as capillary columns. What kind of differences can we expect between the packed and capillary columns? Here we can see that capillary columns are more effective. The main reason is it is much longer compared to this one. If the maximum length of the packed column is up to 5 meters, and here in most common practice, it is around 30 meters. Yeah, so we can observe this kind of not fully separated peaks of compounds, and here in packed columns, and here we can see the fully separated fractions in capillary columns. And in packed columns, we can observe this kind of broad peaks, and sharp peaks are observed in capillary columns. Therefore, the capillary column might provide high detection sensitivity. Okay, packed columns produce broad peaks, and capillary columns produce sharp peaks. In addition, capillary columns produce taller peaks, yeah, which allows the detection of lower concentration, high detection sensitivity. This is advantage of capillary column. So if the quantity is limited in your sample, if there is an option to select the gas chromatographer, so it's better to choose the one with provided with capillary columns. And here we can see the linkage between type of solid phase and temperature, application, separation characteristics, and others. Methyl silicon uh, is a compound with a non-polarity nature, and its boiling point differ from others, and the operational temperature of the, let's say, column provided with methyl silicon ranges from 60 with minus to 360 centigrade, and the one that provided with phenyl methyl has higher polarity compared to methyl silicon. This material is slightly polar to moderately polar, and phenyl groups in it retain aromatic compounds. So phenyl methyl provides some, let's say, affinity to aromatic compounds, uh, and the application for this kind of, let's say, material uh, is in separation of perfumes, environmental compounds, aromatic compounds. Yeah. Operational temperature is very close to the one provided with methyl silicon, uh, which ranges from 60 with minus to 340 centigrade. And cyanopropylphenol is another compound provided with higher polarity. The polarity level is from moderately polar to strongly polar for compounds. And it is effective at separating oxygen-containing compounds or isomers since it has phenol, cyanopropylphenol. So here we can see the linkage that phenyl methyl has specificity for aromatic compounds, phenyl groups, and phenol has cyanopropylphenol has specificity for oxygen-containing compounds. And the operational temperature is between minus 20 centigrade to 280 centigrade. Trifluoropropyl has, let's say, a moderately polar and strongly polar polarity, and it specifically retains compounds that contain a halogen, since it has three fluorine, and the operational temperature is between minus 20 centigrade to 340. And polyethylene glycol is another material that's used in this intention. It is quite strongly polar, and it retains the polar compounds, and it's applied in separation of polar compounds, solvents, perfume, fatty acids, and methyl esters. Operational temperature is between 40 to 250 centigrade. So by the operational temperature, um, it's not as effective as this one that could be used at frozen temperature range. Here we can see some examples, model examples, and SEM figures of how the inside of the column look like. This one is a packed column filled with those sorbent materials, and this one is open tubular with a solid phase is an embedded layer, and this one is a kind of new configuration with solid phase embedded in microchannels of ceramic hollow fiber membranes. And here we can see the SEM photos in B, E, and F parts of the figure. The E one is, as indicated here, the cross-sectional view in which the dashed line highlights a microchannel capsuling molecular sieve. This is microchannel capsuling molecular sieves. So the compounders, volatile compounders, should pass through these channels based on the interactions, the flow of those compounders by nitrogen or helium or hydrogen will be faster in some compounds and will be slower based on the interactions. If the sorbent and the compound has kind of higher polarity. Um, that could be suitable for polar compounders. If the compounds are non-polar, for them some non-polar solvents could be useful to retain them. So these are the figures that we can understand how the separation is how the separation occurs. Again, I recommend you to watch the chromatography videos. I'm not going to repeat those things again. Based on the functional groups of the materials that are used in the matrix, we can expect faster or slower movement of the compounds to be separated inside the columns. Okay, good. So different this kind of structures we can observe in the columns. Yes, so they provide the compounds to be uh, moving faster or slower. And these are about the detectors. Thermal conductivity detector is the first type of the detectors which are used in gas chromatographers. And the second one is flame ionization detector. And the third one, this one is electron capture detectors. And the most common detector is the mass spectrometer. If the gas chromatographer is linked to mass spectrometer, so this kind of tandem of tools can provide more, let's say, facility to identify different volatile compounds. Since mass spectrometer has its own database, uh, so then we are able to identify some compounds based on the database of compounds. Okay. Now about applications, advantages, and limitations. Gas chromatography can be used in drug analysis. If the compounds are volatile, okay, we can use gas chromatography very effectively. It can be used in environmental monitoring to say, let's say, to see the concentration, for example, carbon dioxide or some other gases like sulfur dioxide, sulfur trioxide, sulfur dioxide. Yeah, it is widely used in food analysis for for fatty acids, for example. Yeah, in foraging science, the advantage of the GC is it provides high resolution. The analysis process is quite fast. Uh, it has high sensitivity. It's provided with high sensitive detectors, and they can be well uh, reproduced. And the limitations include that it deals only with volatile compounds. Thermal stability is required for the compounds since the process is carried out in high temperatures. And another limitation is sample preparation takes some time and protocol, let's say. And in summary, we say that gas chromatography separates volatile compounds based on the vaporization and partitioning, and it is widely used in many scientific fields, as we talked here. And here we can see how the compounds can be identified based on the database, for example. These are the mass spectral spectra of corresponding monocyclic and polycyclic TMS metabolites indicated by an OS1 to 16 were depicted in the photo here. 1 to 6 are shown. Yeah, 1, 1, 2, 3, 4, 5, 6, not 1 to 16, 1 to 6. The results were taken from the paper named Analysis of Phenolic and Cyclic Compounds in Plants using derivatization techniques in combination with GCMS-based metabolite profiling. So, if we obtain this kind of molecular weights like 77, 105, 135, or 179, so then we can find out from the automatic analysis, we can find out that these molecular masses belong to benzoic acid. Or we can find molecular mass like 73, 91, 126, 193, yeah, and 207, 223, 267, or 282. So that we can make a conclusion that these molecular masses belong to 4-hydroxybenzoic acid. Okay, this kind of things can be found by operating from the database of the GCMS. So then we can find out the molecular masses of one compound, and then we can suggest the structure and the chemical formula of the compounds based on this kind of signals. Therefore, gas chromatographers can be quite effectively used in identification of different compounds. Next. And here, this is another example from a published paper from MBPI journal. The paper is named Study of the Volatile Constituents in Radix Flamingia, microphylla, and substitute by gas chromatography, mass spectrometry, and chemometric methods. This this spectral data were provided in that paper. It belongs to resolved mass spectrum of component 4 by SFA and standard mass spectrum of I don't know the name of this Greek letter, yeah, Z, yeah, Z cardinal. And the conclusion of the authors were like this. In this work, they combined the chemometrics method, sub-window factor analysis, and spectral correlative chromatography were used for analysis of the volatile constituents in two different plants, one of its common substitutes. So the authors combined two methods here in this work: gas chromatography, mass spectrometer, and chemometric methods. So by combining those kind of methods, it could be possible to obtain more data and interpret the results with, let's say, higher, clarity. Okay. Okay, the study showed that the application of this combined approach is a powerful tool which comprehensively reveals the quality and quantity of chemical constituents of traditional medicine for effective evaluation of similarity or differences between complex analytical samples. The point is, by obtaining different, let's say, by comparing different extractors, it will be possible to compare the profiles of different extractors. So then it could be possible to make some conclusions about the optimization of some of the extraction methods. Okay, next. And in this paper, in this figure taken from the paper named Development of a kaolin-based Bacillus velezensis BF01 composite for application in biocontrol of post-harvest strawberry diseases. We can find out the profiles of extract, let's say, gas chromatography, mass spectrometry, identification of compounds in volatile organic compounds of Bacillus velezensis BF01. The A1 is, this one is total ion chromatography of volatile organic compounds. The second one is composition of VOC. The percentages represent the proportion of the substance in the total amount, and the numbers in parentheses indicate the types of substances. So based on this kind of figures, we can make a conclusion that we can obtain this kind of figures and we can develop this kind of, let's say, belongings of compounds to different classes. So then we can compare to different extractors, and we can compare not only one classes of compounds, but also classes of different compounds into different extractors. So then the profiles of different extractors could be compared, and by developing this kind of approaches, it will be possible to compare, let's say, day-dependent changes of extractors, yeah, time-dependent changes in one day, for example, before noon, afternoon, at night, yeah. So then the extraction of fresh extractors of compounds can be also compared, so some kind of conclusions can be made about the efficacies of extractors that were taken from the plants materials taken in different times of the day. Okay, in general, gas chromatography is very, let's say, effective in these terms. Here we can see the comparison of HPLC and GC, um, which can help us to find out to choose the right chromatography method. Mobile phase in HPLC is methanol, water, and acetonitrile, for example. Yeah, operating temperature is about 20 to 40 centigrade. And in gas chromatography, the mobile phase can be helium, nitrogen, or hydrogen. And the operation time is quite high, 150 to 300 centigrades. Yeah, and operating pressure also differ quite much from each other, as indicated here. And the column in HPLC is kind of short, small, with the length up to 25 centimeters. And in gas chromatography, the column length can reach 100 or 150 meters. But in general, it is about, let's say, 30 meters for capillary columns. And the analysis speed. Uh, Analysis speed in HPLC is between 10 to 60 minutes, yeah, in general 20, 25, 30 minutes. And in GC, it is seconds to minutes. It's much shorter compared to this one. And ideal compound types here in HPLC are non-volatile, polar, heat sensitive, yeah. That could be proteins, vitamins, other biologics, active pharmaceutical ingredients. And for GC, they could be hydrocarbons, solvents, yeah, volatile organic compounds, aromatic compounds, and so on. And the molecular range in HPLC can be wider compared to the GC, as shown here. And the cost profile. In HPLC, the analysis might cost much more expensive compared to GC, because of the mobile phase here is non-expected gas like nitrogen or hydrogen. Let's exclude helium in this case. But in HPLC, the mobile phase includes methanol, acetonitrile, which are quite expensive. Okay, and the key applications for HPLC include pharmaceutical active ingredients, biologics, yeah, vitamins, metabolites, and pesticides. And GC can be mainly used for volatile aromatic compounds in pharmaceutics or food industry or chemical industry. Besides, GC can be effectively used for residual solvents analysis or volatile organic compound analysis, hydrocarbons and fatty acids analysis, and others. So these are about the comparison between HPLC, high performance liquid chromatography, and GC gas chromatography. These are all. I hope you had some useful information from this video lesson. To those who watch us on YouTube, I kindly ask you to support us with your likes so the video lessons can reach wider audience. To be a contribution to our development. Thank you for your attention. Have a good day.